Welcome to Kinetic Energy Basics, Physics Lesson 8.1. Okie dokie artichoke, let's get started. So, conservation of energy. Total energy in an isolated system all by myself remains constant. What that means is as long as the system remains closed, so nothing coming in, nothing coming out, then the energy that was in that system stays there. The only thing is it transforms from one thing to another. So maybe going from, wait for it, kinetic energy to potential. And these are both measured in joules. How about that? All right, so let's look at kinetic energy first. So kinetic energy is the energy of motion. So whenever an object is moving, it has kinetic energy, and whenever it's not moving, you guessed it, no kinetic energy. And that means one of the main things that we're going to look at when we're looking at kinetic energy is how fast that object is moving, or that object's velocity. So it just so happens that our kinetic energy formula, kinetic energy, is 1/2 our mass times our velocity squared. And that means that kinetic energy depends on mass and velocity. The more velocity, the more kinetic energy. The more mass, the more kinetic energy. All right, so let's see if we can put this together in a couple of our practice problems here. All right, first we have Binks, the cat. Binks has a mass of 3 kilograms. Right there. So 1/2 our mass, 3, times our velocity, 4 meters per second, squared. That should give us 24 joules of energy. Then there's Duper, who has a mass of 6 kilograms. So now we have 1/2, 6 kilograms, still going at 4 meters per second, and he should have a kinetic energy of 48. Right? 1/2 the mass times velocity equals our kinetic energy. Even though they're traveling at the same velocity, because they have different masses, they have different kinetic energies. Alright, so let's just say, I don't know, hypothetically, Binks realizes she doesn't like Duper very much. Aww, it's not nice. So she begins to run away at a rate of 8 meters per second. So what's her new kinetic energy? Well, 1/2 our mass is still 3. 8 squared. So now our kinetic energy gets bumped up to 96 joules. More kinetic energy. Higher velocity, more kinetic energy. Alright, well, let's see if we can do it another way. So let's say that Duper bumps up, bump it up, his kinetic energy to 300 joules. So he has 300 joules. His mass is 6 kilograms. I'm looking for his velocity. Alright, so 300 joules equals 3b squared. Divide each side by 3. 100 joules equals b squared. Or in this case, it would just be meters per second squared, but whatever. Square root, and we're left with 10 meters per second equals our velocity. So how fast is he going? 10 meters per second. Alright, let's go through some potential energy stuff. Alright, first, potential energy. Energy that's stored in an object. And there's 4 basic types: gravitational, elastic, electric, and chemical. And more often than not, they get transferred between. So potential converted to kinetic, or kinetic converted back here to potential energy. So that's fun. That happened. Alright, Gravitational potential energy. This is the one that we're mostly going to see. Um, this is whenever an object is at a height. So the greater the height, the more gravitational potential energy. The lower the height, the lower amount of potential energy. Formula-wise, we have gravitational potential energy equals our mass times our acceleration of gravity, which is 10. And we can leave it as a positive number. Hold on just a second.
Amanda?
Sorry about that. There was a announcement on the PA. All right, and then H, that stands for our height. All right. In each one of these cases, the object should eventually fall, thus turning their potential energy back into kinetic energy. All right, so let's give a problem out here. Let's say, hypothetically, we have Sally and Billy Bob, and they're on a date. And Billy Bob takes her to this brand new, super scary film, A Life in the Day of the Teacher. Very scary. In order to get the best view, they sit in the first row, which is 4 meters high. So, mass of Sally, mass 1 equals 90 kilograms. Height equals 4. So for Sally, or mass 1, as I like to call Sally, it should be 90 times 10 times 4. And that should equal 3,600 joules of energy. Then, let's take a look at Billy Bob, or what I like to say is mass number 2. He has 40 kilograms, and the height is still 4 meters. So, let's extend the page a little bit. 40 times 10 times 4. And that should be 1,600 joules of energy. So, Sally, more massive, has more potential energy given the same height. But let's say, hypothetically of course, that someone is behind them and he is 3 rows up. If he has 7,200 joules of energy, then how much is his height? Right? So we have 7,200 divided by 1,200. Right? 120 times 10. 1,200 cancels out here, cancels out here. The height should equal 6 meters. Smiley face, or frowny face, considering he's a weirdo. Alright, so other types of potential energy. So we have elastic potential energy. Yeah, this is anything that is stretched or smooshed. It's elasticy. By pulling something apart, you are giving it more elastic potential energy, and then that can get converted to kinetic energy. Electric potential energy. This is anything in a battery or power source. And then there's chemical potential energy, which is anything that's stored in the composition of an object. So chemical makeup, gasoline, sugar, anything that can really be burned to generate more energy or transfer the energy from that chemical bonds to something else, like in thermal or light or sound, anything like that is going to be chemical potential energy. Alright, so that wraps up the basics. I will see you next time. Same physics channel, same physics time, or not. You can literally watch this anytime you want, or not watch it. I don't know, whatever. Okay, see you later.